got this morning is Anders Hansen, and he's going to speak on compressed sensing in the real world for a museum.
Thanks very much, and thanks so much to those who got up early this morning to come and listen to my talk. I'll be talking about compressed sensing and the need for a new theory, and when doing that, I'm going to motivate this with some applications. So here I have a list of applications that you can use compressed sensing. Some of these problems, compressed sensing, are used with great success. Some of them has the potential for compressed sensing. And I start with maybe the flagship for compressed sensing in applications, maybe namely MRI. There's other areas of medical imaging, such as X-ray computed tomography, and of course all the different cousins that you have there based on roughly the same ideas. So this covers a lot of medical imaging. Then you have, say, electron microscopy, for example, which is a very different thing than medical imaging, but based on somewhat similar ideas. This is also based on the Rodon transform. Reflection seismology, big field for oil companies who would like to know where they should drill. Radio interferometry, it's a part of astronomy. You're interested in taking pictures of stars and galaxies. This is again quite different from these, much closer to MRI. This is actually based on the Fourier transform. And then at the very end, fluorescence microscopy, which is very different again from electron microscopy. This here actually uses lenses. So why do I show you this? Well, first of all, this is a workshop on inverse problems. And most of these problems, with the exception of the last one, fluorescence microscopy, can be described in a sort of analog or infinite dimensional way, typically by the Fourier transform, MRI or radio interferometry, and Rodon transform, a lot of the other tomography issues. The neat thing is that in many cases you can recast this to the Fourier case with the Fourier slice theorem. So you boil this down to one inverse problem where you essentially see G, which is the Fourier transform of F. And in some cases you need to sample this then according to radial lines if you do the Fourier slice. But essentially you're interested in recovering a function from samples of the Fourier transform. So why do I mention this? Well, first of all, it is important to have Fourier measurements. That is something that we are interested in a lot. But I want you to keep in mind that all these problems are analog and infinite dimensional, and that is important when we discuss issues with compressed sensing. If you have never heard about compressed sensing before, I'm going to give you a short introduction to what that is and sort of point out the pillars of compressed sensing. So compressed sensing is usually said in a finite dimensional setting, which sort of contradicts what I already shown you with the problems which are infinite dimensional. But anyway, let's start here. So typically you have a matrix. Here is the unknown x0, and here are the measurements. Now, solving that is not really rocket science, and that's not what this talk is about. The idea with compressed sensing is that maybe you don't see all the observations here. You have some projection, I'm going to call it P omega, and that omega here is chosen according to some randomization of these indices 1 to n, and then we're trying to solve this underdetermined system and figure out if we can actually recover the original guy. And if U is an isometry, and I sample here uniformly at random, then the number of samples that you need to draw are described by this. There is a uniform constant here, the dimension n here, and then you have this mu of U, which is called the incoherence parameter, and that is simply the maximum values of the matrix elements squared. The S here will be the number of non-zeros in the original guy that you would like to recover. And then there's a log epsilon factor here that comes into the estimates for the probability of being able to recover, and then log n of the dimension. So from this equation here, you can essentially read out what the pillars, if you will, of compressed sensing is. The first is what we call sparsity. You can see that from here, the number of non-zero elements. That's your S. That's a key thing. The second one is the incoherence. You desperately want that parameter here to be small. Typically, you want that to be 1 over n, so that kills that thing. If it isn't, if this, for example, was 1, there's not very much subsampling you can do. And of course, this is done with uniform random subsampling. In addition to that, there is something called the restricted isometry property and uniform recovery, and I'm going to comment on that later on. So this is all very good. That's fine. The only problem is that on the list of problems that I showed you before, virtually all of those, these concepts here, are completely missing. But yet you can actually use compressed sensing in a lot of these problems. So what we have now is essentially a large part of the engineering community using compressed sensing, but we can't actually explain that with the current mathematical theory. And that is what this talk is about. I'm going to start with a very, very basic example from MRI.
Where did the name come from?
Pardon me?
Where did the name is not consistent with the pillars.
A compressed, compressed sensing? It started, I think, in the beginning where one essentially said that if we are going to throw away a lot of information because we're going to essentially compress at the end, why do we take all the information? Suppose that I take an image from you now, and I'm going to compress it afterwards. Why do I need to take all those measurements? Because I'm going to throw away 90% of it afterwards. So the idea was that if you have a clever way of measuring it, then you can take fewer sample, and essentially you're compressing as you're sensing. So that was sort of the initial idea. So I'm going to show you a very, very simple example from MRI. And you may say, well, when I do this here, I say I have a discrete Fourier transform and discrete wavelet transform. MRI problems are not discrete, and that's certainly true, and I will comment on that later on, but I'm going to keep the simplicity here. So this is simply a discrete Fourier transform and discrete wavelet transform, so this is a matrix. So that's now the U matrix that I have in my reconstruction problem. What I'm trying to do now is that I'm trying to do a recovery of something. I am sampling here 5% uniformly at random. And it's a little hard to see this because you have tiny small dots here, but it's 5% spread over the whole frequency plane, or well, parts of the frequency plane. This is the reconstruction, and you may ask, what on earth is this guy trying to reconstruct? Well, I'm actually trying to reconstruct that brain image, not very successfully though. What I could do instead is that I could take 2.5% dense in the middle, and then do 2.5% uniformly elsewhere. Now, suddenly we can actually see what we're trying to reconstruct. It is not all that great, it's okay. I could have thrown in a different sampling scheme. Looks a little bit more like a cloud, dense in the middle, but different from this. And then you can see, can you see that? There's much clearer things here than there. So why is this? I have 3 very different sampling schemes. One gives garbage, some of them give reasonable things, some pretty good. So the question is, why does this happen? What we can certainly learn from this is that uniform random subsampling may not be what you actually want to do. And we're going to talk about that later on. Yes, all of these here act exactly the same algorithm, but different sampling schemes. So different p omega, but very, very different sampling schemes, but exactly the same amount of information. Okay, so that was uniform random subsampling, which is part of one of the pillars. Now let's talk about sparsity. So sparsity in compressed sensing means that you have S non-zero coefficients, but you don't know where they are. And that makes total sense, right? Why would you like to have a model where you need to know where they are? So the whole point is that the location of these coefficients is arbitrary. Okay, now, does that mean really that in applications that the success of the subsampling schemes that you have are really independent of the location of the coefficients? Well, it's a very easy test to test this. We call it the flip test. Again, I'm going to do a very simple example from MRI. Here is my unknown. It's my brain image. I call it X. My measurements is the discrete Fourier transform acting on that X. That's my Y. I pretend, or I think, that this here is sparse in some wavelet basis, so I use a discrete wavelet transform to make it sparse. I sample according to some rule. I'm not going to do uniform random, which we saw was crap. And I'm going to solve this. So here is the matrix that I end up with. And what we're going to try to see is, would the success of the sampling schemes that I try, are they going to be independent of the location of the coefficients? So what we do is the following. Here I have 2 reconstructions. They are using 10% of the Fourier information. So I'm doing 10% subsampling. And I haven't done uniform at random because that gave garbage, but I have subsampled here according to 2 different distributions with slightly different decay. And this is what I get. Not too bad. Looks pretty good, right? Now, what I'm interested in is, did this actual success happen independent of where the locations of the coefficients are? Here you can see the coefficients. This is done in dB8. Here are the wavelet coefficients, and they look like this. So what I'm going to do, I'm simply going to flip them, right? So I flip them, and then I take exactly the same matrix. That's the key thing. Now I have the flipped coefficients. That requires new measurements, but it's the same matrix. I use exactly the same subsampling, because I wanted to see if the previous subsampling was independent of the coefficients. Then I solve this. If it is indeed independent of the location of the coefficients, I should be able to recover here and then flip it back again. Did that make sense? So if I flip it back, it should give me the same thing, right? What do you think happens? Would anybody like to guess? You get somebody's really hungover brain at best. So maybe the location of the coefficients actually did matter. So now you think this guy is probably a complete lunatic, right? Because this goes against the whole message of compressed sensing. Maybe this is a completely contrived example.
Can you for a second elaborate
Yes.
for a second? Because if you change the location of the coefficient, did you go to perturb the column A as well?
No, it's the same. It's completely the same thing. I'm using the same matrix. I'm checking if my subsampling scheme would work for a different constellation of coefficients. It has the same sparsity. I'm just putting it somewhere else. I'm flipping it.
Yeah, but the sparsity of different coefficients means different coefficients, isn't it?
No. It's exactly the same thing. It's this.
Okay. I'll ask you later.
It's exactly the same thing. I just flip it. So the sparsity is exactly the same thing.
The matrix A have to change as well, correct? If I don't order them in a different way, I have to reorder my A.
No. The whole point is that I want to check if my matrix, if I can recover regardless of the position of my non-zeros. So I don't change this. This is the whole thing.
The non-zero values are the same.
Yes.
Are the same.
It's exactly the same thing. I simply flip it.
But the data will be different, right?
What?
The data will be different.
The data will be different.
Yeah.
Yes, of course. I'm creating a new one here. It's a completely different thing. That's not what I'm checking. I'm checking if my recovery algorithm can recover regardless of the location, right? So I saw here, this location here, I could actually get it. But with a vector that looks like this, I would get this.
But the coefficients imply some basis function which may be hierarchical in some way, correct? Or
No, it's the same basic function. It's dB8. It's exactly the same thing. I have exactly the same vector, but I'm flipping it, right?
But you've kept the same probability density for the sampling.
So it's exactly the same sampling pattern that I've used. That's the whole point. Because I'm checking if my sampling pattern is valid. So I want to check if my sampling pattern can actually do this regardless of the location of the coefficients.
Saying that if you have some prior information about the coefficients, that should decide your sampling.
Exactly, but I'm not finished with this. I'm going to show you several things. So the question here is that, is this now just an example that you will, for example, see in MRI? So you can take some other fields, like, for example, fluorescence microscopy. In this case here, you would not use the DFT, but say a Hadamard matrix. Here's a subsampling pattern that I can use. It's a pretty good recovery. I do exactly the same thing, and I keep exactly the same sampling pattern and exactly the same matrix. I just flip the coefficients. And then I get garbage. I could do this in compressive imaging or Hadamard spectroscopy. It's the same thing. This is a very different sampling scheme than that. I can recover very well. This is with 12%. I flip the coefficients, and it doesn't work. It's the good old MRI again. Here is a sort of a cloud. This is a different subsampling pattern that I used before. Here is the reconstruction, and here's with the flipped coefficients. If I do tomography, for example, or electron microscopy, I don't have any randomness. I will simply sample according to radial lines. I can recover reasonably well. Again, if I flip the coefficients, you get garbage. Finally, radio interferometry, which is also based on the Fourier transform. There you have the original, well, this is actually the reconstruction, 10%, and here is the subsampling pattern, again very different, and I flip the coefficients. So the key thing is that the success of your sampling is actually dependent of the location of the coefficients. And more importantly, the optimal subsampling scheme depends on the structure of your signal. And that's the key thing. So if you're going to have a theorem describing this, you cannot have sort of S log n. Your theorem must reflect, essentially, how your sampling scheme will have to differ with different structure on your signal. That's the key thing. So I haven't talked about the RIP. The restricted isometry property is something that you have of a matrix, so that it essentially looks like a local isometry. If you have that property, it doesn't matter where the location of the coefficients are. So the question is, did any of these matrices actually satisfy the RIP? And they didn't, because if you have the RIP, you can flip the coefficients. Okay, so now you may ask, what on earth is really going on? Because if this actually works, yes, please. For what?
RIP is a sufficient condition.
It's a sufficient condition. It's never necessary.
Condition. So,
yes.
So it doesn't necessarily imply the other way around, right?
Yes.
So
the whole point is that a lot of the stuff that we have in compressed sensing is based on RIP, and it's therefore convenient to check. Do we actually see the RIP in real life? And in these cases here, you don't see the RIP.
Well, it still doesn't imply that
It doesn't imply that you cannot recover, which I showed you that you can. Yeah, you indeed can. But you cannot recover with arbitrary, essentially, structure of your signal. That's the key thing. So then you may ask, what on earth is really going on, and why is it working then? So the reason why is that the world isn't sparse. It is asymptotically sparse, and it has a lot of structure. So, for example, if I take my F and I expand that in a wavelet decomposition, well, wavelets and all their cousins, say shearlets, curvelets, contourlets, and your name itlets, have a very specific structure. You can talk about wavelet scales. So you can essentially order this into different levels. So what I'm going to do is that I'm going to take my natural numbers and simply put them into sort of a level structure. These here are going to be, say, the wavelet scales, for example. And what I'm interested in is essentially the relative sparsity corresponding to these different scales. So what I'm doing is that I will take, say, an epsilon between 0 and 1. And my sk now is essentially the number of coefficients that I need to see in that scale if I order them in descending order so that I can get greater than or equal to epsilon fraction of the energy of the signal there. So I'm essentially dissecting my signal into a sort of part where I look at it there, and I look at the relative sparsity. And the reason why I do this is that because this here is very, very easy to measure and plot. So here I have two very different images, brain and a watch. And what you see here is essentially these sk divided by the length of that level, if you will. So the relative sparsity. And if I fix an epsilon and take larger and larger k, this is what I see. So it actually tends to 0. So when I go further and further out in the expansion, the signal becomes sparser and sparser, if you will. It does so even in a sort of uniform way. So this here would be sort of the worst kind of sparsity I would have. That means that all the values in that level have the same value. And the best thing would be something which is flat. So here we can actually see that it becomes more and more flat. And it gets closer and closer to sort of perfect sparsity. But note the following. Note that this structure here is very, very close to what you have here with very different images. I can do this with any other of the cousins of wavelets. You can do this with curvelets. That's the same. Here you have the brain image. Here you have the watch. Curvelets, contourlets, and shearlets. And they all have a very specific structure. You have not very sparse in the beginning, and it becomes more and more sparse. And that is the structure that you have of images. And that is the key to the success. But you need to know what you're doing, and you need to tailor your sampling scheme to this. So that was a little bit about sparsity. Now I'm going to talk about incoherence. So remember, I'm just going to flip back so you remember the statement. remember this. We want that desperate to be 1 over n, so that that cancels that. There's one catch, though, and that is if I take the discrete Fourier transform and the discrete wavelet transform, that incoherence is 1 for all Dobrashev wavelets and all n. It is completely coherent, which is not good. So then you may say, okay, of course there's something wrong with the Dobrashev wavelets. What we have to do is to cook up some new wavelet system that may be more incoherent, if you will. And here is really the key thing. That will never work, because essentially analog or infinite dimensional problems that we're discretizing here will always be coherent. And you can see this with a very easy argument. If I take the weak operator topology limit of this matrix here, by weak operator topology I mean the limits as the matrix elements converge, I actually get this infinite matrix. And this infinite matrix here contains inner products where I take, say, some psi's here. They would be the complex exponentials, as in Fourier measurements. And these phi's here would be the wavelets. And the point is that this here has a fixed coherence regardless. So if this here actually converges to that, what that means there will always be a barrier. There's also always going to be some C, which I will never break. So the key thing is that if you're considering an inverse problem, which is really infinite dimensional, you will never have this nice incoherence. So what saves the day then? Why does it actually work? And this is why it actually works. Because although the world is typically completely coherent, it is asymptotically incoherent. So here I plotted this matrix that takes us from Fourier to dB4. And here is what you see. White is 1. The white is bad. Black is good. Black is 0. And here is the 1 that you get. It's completely coherent here. But it actually gets darker and darker the further out you go. So what actually happens is that when you look at the signal and you have that sparsity pattern, it adds completely up to what you have here. When things are not sparse, it is also not incoherent. But when you go further and further out, it becomes more and more incoherent, and also your signal becomes more and more sparse.
Depend of the base, so you don't need to have wavelet base for this here.
Well, that's a very good point. That's why I put this one here as well, because this is the case if I go from Fourier to Dobrashev 4. Now look what happens if I plug in Legendre polynomials instead. It's a completely different pattern. It's actually a quite nice mathematical puzzle to figure out what is the decay here. And the decay is actually 1 over n. It is perfectly asymptotic. Here it isn't. And that's not something that you can deal with. It's given, say, by the great mathematical Lord. We just have to discover it. For wavelets, you can actually make statements. So all wavelets are going to look like this. All different kinds of polynomials are going to look a little bit like that. But this is also something that you need. I'm going to show you estimates. So you need to actually know what is going on here to be able to show how you get the optimal sampling strategy. Another one. So this is not a Fourier case, but a Hadamard. A Hadamard matrix is very useful in a lot of what's called compressive imaging. You may have heard about the 1-pixel camera or the lensless camera. And the idea is that you're essentially measuring with 1s and -1s, hence the Hadamard matrix. Problem again, this is completely coherent, yet it is also asymptotically incoherent. Now check out. So this is Hadamard to Haar, very close to the pattern that you saw before. This is Hadamard to dB8, quite different, but the asymptotics are the same. We can actually compute what that is and analyze it. Okay, so the whole point is that we need a new theory to be able to actually express what is going on with compressed sensing in real-life experiments. And such a theory must be able to explain 2 phenomena. The first one is that the optimal sampling strategy depends on the structure of your signal. That's the key thing. If you flip the coefficients, you may get garbage. The other one, which I'm also going to address at the very end, is that the success of compressed sensing is resolution dependent. If you do your experiment at a low resolution, you can get garbage. You take exactly the same experiment and blow this up, and you get fantastic results. So lastly, this cannot be based on the RIP, because the RIP says essentially that I don't care where the coefficients are, it will work regardless. But in these cases here, that's not the case, so you cannot have any RIP. Okay, so how should this theory be then? So given that a lot of these sparsity basis or frames that we have are based on levels, maybe we can essentially try to adapt to that. So what I will do is that I will say that instead of having just, say, one level, I'm going to have R levels. And within these levels, I'm going to have a sparsity vector S, but that contains an S1 through SR. And the whole point is that I'm interested in looking at, say, the structure of these things. So I say that I have an SM sparse vector. So if the support of my beta, which is an L2 vector, that the support here in that level is then bounded by SK. And then we set this SM sparse vector to be this sigma S of M. So there's now two vectors. There's an M vector, which is the levels, and then you have an S vector, which are the sparsities in those levels. And then what we define is now what we call the SM term approximation. So that means that I can approximate here with the best element that I have, which is SM sparse. But this is very different from what you will normally refer to as the S term approximation, because this has a lot of structure in it. That's the key thing. So you cannot flip, but you're able to flip within the levels.
You need all the components of these vectors to do it, or you can do it just?
No. This is the reason why I do this here is that I will show it in the estimate, because when I'm going to try to recover vectors, they're not going to be perfectly sparse. They're going to have a tail. And what I'm going to show is that the best thing you can do is going to be bounded by this. But it cannot be the S-term approximation, because the S-term approximation would be any kind of pattern, which you clearly can't, because then you would be able to do the flip test. Yeah. So then how do you sample them? Well, we're also going to sample according to levels. So these levels could be exactly the same levels as you would have in the reconstruction basis, but they don't have to. So I have N1 through NR, so these are the levels where I'm going to sample. And here's the key thing. I'm going to have then M1 to MR, which are now going to be the sampling densities in these different levels. So I'm going to essentially say MK, which is now smaller than NK minus NK minus 1. And then this here, this omega K, is now a set of indices here in this set, so that the size of this is MK. So they can be very different. And the whole point is that we're going to tailor those according to the local sparsity and the local incoherence to get the optimal sampling strategy. And then your total sampling, your omega, is simply the union of all these different things. Then we also have local coherence. So the local coherence, now depending on both the sampling levels and the reconstruction levels, is this. They can be the same, but they don't have to be the same. So here is the local coherence. So what I take is that I take my matrix, and I dissect it, if you will, from each part. So this projection here projects onto the first ML minus 1 to ML, and I do that on the same thing on the left-hand side. So this takes essentially different sections of that matrix, and I look at the coherence where it is. So this matches exactly this. So I can look at the different coherences here, not the global one. And then obviously we solve this and we allow for noise. So we can have a delta level of noise there as well. And here is now the theorem. We always do everything in the proper infinite dimensional way, but I'm going to show you sort of a finite dimensional corollary of this. And here's the key thing. In each of these levels, I need to sample according to this. And instead of having an S log n with the coherence parameter, I have now these local sparsities matching with this local incoherence. And now you see the key thing, because if I swap this, I would have a different estimate here. So if I change the location of these SKs, I will have to change my sampling scheme as well, which is exactly what you see in practice. There's one problem, though, and that is that when we give up this sort of S log n, it isn't as pretty. And there's one extra condition, and you can't get away with that. This have to be there. We can show that that's right. You get an extra condition, and that means that these SK tildes here are actually not these guys here. And this here is quite delicate. And the reason why that happens is that if your matrix was essentially a block diagonal, everything would reduce to this. But you do have interference from all the different levels, and that's why this is actually a quite hard thing to prove. So these things here can be estimated by this. I'm going to show you that on the last slide. But if your levels are matching those equations, the eventual error that you will get is this. And here's the key thing. You now have the SM term approximation. It is not the S term approximation, it is the SM term approximation, where the structure of that is buried. So that means that I cannot flip, because this here tells me about the structure of that S and that M. And then you may say, okay, what about these awful guys here that bounded these tilde S case? It looks really horrendous, and it is a little horrendous. But the point is that you can actually estimate this. So all this abstract nonsense can boil down to this estimate here when you do wavelets, and that is much crisper. If you're sampling, you let your sampling levels be exactly the ones according to the wavelet levels. Here is what you have to do if you go from Fourier to any wavelet. These log factors here, and then your MK is going to be dominated by the SKth level and the neighbors, the closest neighbors. And then you're going to have an exponential decay of the neighboring levels. And that actually goes down, so this alpha depends on the decay of the Fourier transform of the mother wavelet. And this is the number of vanishing moments. So the smoother wavelet you have, and the more vanishing moments you have, the closer you essentially get to a block diagonal structure, if you will. If this was perfectly block diagonal, these things here would vanish. So this is what's going on. And this tells you essentially how this gives you almost optimal recovery guarantees, even though this matrix is completely full. It is never a block diagonal. Yes?
It's still there. Is that the point?
In this case here, we have, so what brings us this is that this is paint by numbers, because this we have, and this we can just plug in. But to get these estimates from that, we have to know what that is. That is this awful looking thing here, and when you say, oh my God, what is this? But the point is that you can actually deal with it. It takes, you know, a good number of pages to get it, but you can do it. So the point is that this abstract framework here allows you, when you can do things with this, which you can, to get estimates like this.
I see.
Which is, in that sense, near optimal. Because if it was block diagonal, all these things would vanish, but you actually just have an exponential decay, and when you have more smoothness and more vanishing moments, they decay even faster. Okay. So, yes, please.
Makes sense to, I mean, you're minimizing L1. Would it make sense to have some weights depending on your structure?
That could be, but that will be a very different algorithm, though. So that is possible. You can have weights on it. But so that's actually a very valid point. But what we're doing here is that we like to essentially explain what is going on right now. So the existing thing. So there's a huge engineering community who's running. They are running this very happily. And we want to say, okay, the reason why it works is because of this.
Okay.
Yeah. Because what people are doing is that they are essentially trying this with a lot of different ways and saying, oh, it actually works. I have no idea why, but it works. And that's totally fine. But as mathematicians, we need to understand why. So you can certainly do a weight on it, but that's a completely different algorithm. So if somebody can say, hey, if you do a weighting thing and you can beat that, let's go for that as well and analyze it. But now we're dealing with what's out there. So this is how a R-level sampling scheme may look like. This is a 2D thing in MRI. You have dense samples in the middle. The next one here, slightly less, and then it goes down like that. So you get sort of this cloud. And the point is that the way you choose this optimally will depend on the structure of your signal. So you don't know how your signal will look. So what you have to do is that you have to test. And that's exactly what engineers do. They try this, okay, I have this class of signals, and we're going to try to figure out what is the best thing we can do. And they try and try and try. But there's a mathematical reason why, and that is essentially because of the previous theorem. I probably have, say, 5 more minutes, and then we have questions. Yeah, I'm going to show you just one numerical example just to point out what you can actually do here. So this is a problem in what we call compressive imaging. So compressive imaging is based on the idea that you can create measurements that are either ones and minus ones. So this is the basis for the, say, single pixel camera, for example. And what you can do there is that you can take a random Bernoulli matrix, minus ones and ones. And you can take, say, 15% of the samples, and you can try to reconstruct with L1, and this is what you get. And random Bernoullis are very intriguing matrices because they are what's called universal. That means that it will always have the RIP, and I can change the reconstruction basis to anything I want, and you will have exactly the same recovery guarantees, which are S log M. The only thing that is sort of missing is that it isn't all that great. But this is sort of the holy grail in compressed sensing because you have universality and you have the RIP, and it works sort of well. What you can do is that you can use a Hadamard matrix instead. A Hadamard matrix is completely coherent, as we showed, but you can use a multi-level structure on this, and you will actually get this with the same amount of information. And it's exactly the same type of measurements. The advantage is, well, that you actually get a much better recovery. The other thing is that this here will require a substantial amount of RAM because you need to store the matrix, and you don't have a fast solver. For this one here, you have an n log n solver. So what we can do is that we can blow this up. Now, you see here, now we're getting into the reds because 76 gigabytes of RAM, now we have completely exhausted that one, and also probably my desktop. We can pull this off by using sort of slightly bigger muscles, but when we actually go to this kind of resolution, that can't follow. But a Hadamard, you don't need to store, and you have this fast, so we can do this, and even this, reasonably easily. And you can see here that if I would have to do this with a full Bernoulli, then I would need 5 million gigabytes of RAM, which probably isn't what you can do in this universe, and it would take about 238 days. So, there's a couple of things that I would like to comment on. First of all, if I did a flip test on this, I would get complete garbage. If I did a flip test on that one, I would get exactly the same thing. The mathematical theory is true. This is universal. Random Bernoullis are. But the problem here is then, do we really want that universality? Because universality essentially prepares for the worst case scenario. This one here doesn't prepare for the worst case scenario. It prepares for, well, a typical image. But you can actually get much better with that. But it's not universal. So that sort of begs the question, do we really want the universality, or is it okay to use something like this? Because, well, it is never going to be able to take the worst case scenario, but in the general case, we may not actually want that. This here sort of prepares a little bit like for a nuclear winter. This is more like a rainy day. Before I end, I just want to show you the following phenomenon. Look at this. Look at the error here when I blow up the resolution. It goes down all the way until finally here. And this is exactly what's going on, because if you look at the theorem and you look at these S's, and I showed you that plot, it becomes more and more sparse and more incoherent as you blow this up, right? So that is essentially what you expect. So you cannot have statements like, oh, I can do 10 times speed up or 4 times speed up. It doesn't make any sense. It depends on the resolution, and it also depends on your signal. So it is very important to get through to the applied community that, you know, when you actually test this, and if you test this on the exact same data at a low resolution, you can get crap. But if you blow this up, you will get actually very, very good results. I had a couple of extra numerics, but I'm going to skip that because I just want to go through. In this case here, the resolution is always the capital N, yes. Yes. So I would like to finish with this sort of take-home message. So the first and most important thing is that the optimal sampling strategy depends on your signal. That means that you have to tailor that, and your theorems must reflect that as well. Real-world problems are completely coherent, typically, because they're infinite dimensional and they're analog. So what you have to do is that you have to essentially use this kind of multi-level sampling to be able to fight that. We have covered now the abstract orthonormal basis case, but there's tons of more things to do. You need to cover TV, you need to cover curvelets, all different kinds of frames and polynomials, etc. A very important message for the applied community is that we don't need to strive to create hardware that should give you something which is completely incoherent. It is totally fine. And this is the key thing, because if we actually wanted to have an MRI machine that would actually give us random Bernoulli or random Gaussians, it is not needed. And also, more importantly, you get worse results. So I would actually keep the MRI machine exactly as it is, and we will tailor the sampling. So we're not going to strive to make hardware that will actually give us perfect incoherence. Speed and storage issues can essentially be solved by using fast transform and multi-level sampling in compressive imaging with Hadamard matrices. And finally, I'm going to mention some names and people who are also working on these things. So Kramer and Ward, Barnuik, Chever, Duarte, Hegda, and Calderbrand, Karen, Carson, Chen, and Rodriguez. And with that, I thank you very much for your attention.
Perhaps you should have added also there asymptotic sparsity in this nice take-home message, yes?
Yes, I probably should.
But apart from that, apart from this very, very nice talk, I don't understand now the title of your talk.
Yes.
No, I don't understand.
You don't? No.
After your talk, because your title was that we need a new theory, but it seems that you have presented a new theory.
That's true. So the beginning was that we need one, and then the sort of the tail of the talk was, well, now actually we have one. However, I should say that, so I say that this is volume 2 of compressed sensing. So volume 1 was S log n, and now we're writing volume 2. That's not something that we are writing, it's the whole community. So this is now, the new thing is that we're taking structure into account, and that allows us to boost things and also explain why things work. So that's sort of the second thing.
Oh, it was very, very nice.
The interesting thing is that the world is much more complex than we thought it was. So the mathematical theory that you need to describe this is then much richer than you actually thought at the beginning. So when you read now survey papers now on compressed sensing, you can get a feeling that it's sort of exhausted, that we know most things, but that's not the case. Now we're actually starting to write volume 2 of it. Yes.
So how did you find the appropriate bands when you work for the...
That's a very, very good question. What we're doing here, because the point is that we're not allowed to cheat. So when I do this here, we choose an all-rounder. Because we choose an all-rounder. Because we're not allowed to cheat. If you give me an image and I'm allowed to train on it, you know, and I know I can see where the S's are, I plug that in, you know, and I know exactly what the optimal should be. But the world isn't like that. So the best thing you can do is essentially you need to train. So what we're doing then is that we're taking an all-rounder and say, this is what we think is going to work, and we try that one. And that is based on statistical testing, because we don't know what the images are. But the key thing, and that's why I wanted to show you this, the key thing here is that with very different images, the structure is remarkably the same. So if I take a subsampling scheme that's going to try to recover this one or that one, it's probably going to do reasonably well. I could tailor it so that it will be better on that one and better on that one. But there is one that can handle both of them reasonably well, you see. But it's a very delicate and a very good question. But mathematically, we can deal with it. But in real life, you'll have to do statistical testing, which is what engineers are actually doing.